we're getting into a very different section of the class now, as we're wandering off of quantum mechanics, especially. We're not going to see so much operators, especially operators that go across the board 2 times. What we're going to start doing, I'm finishing up spectroscopy today, and we're going to get into multi-electron wave functions. And for reasons that I'm going to explain after just maybe 5 or 6 minutes, it's very different when you're dealing with multi-electron wave functions. You run into some issues that mean that the way you approach quantum mechanics with multi-electron, helium, basically H minus, basically everything is way different than you do with hydrogen. And then we're going to actually get into a very descriptive part of the class for spectroscopy. And again, that tends to be totally descriptive with almost no equations whatsoever. So it'll be very different. And then we're going to end with kinetics. Let's see here. Now, there was a weird, number 2 on the homework is kind of a weird question, so look for the Extra Friday lecture to see how to answer that. The whole thing was actually a description of answering that question. But that question is answered in words. It doesn't expect you to actually do any calculations. Okay, so back to spectroscopy, but before I do that, I want to remind you of something. I'm tempted to do this on the exam. This is kind of BS-y, but I just want to remind you how this works. Let's say on the exam I say, oh, okay, here's a hydrogen 2pz wave function. Let's say I did that. Is it normalized, right? It's not the best question. Of course you know if you integrate it, it'll come out to 1. Of course you know that. But at the same time, I'm tempted to see whether you can do it or not. Because you know the answer. It should be easy points. But if you can't do it, well, I don't know. Not everyone gets an A, right? Maybe that's how I know. So I just want to remind you how to do that because it is actually slightly more involved to, let's say, even do a simple normalization. Remember that's this guy here, and I said last time that we have symbologies that we use when we're doing multi-dimensional integration. Mostly, as so many times, we have symbologies so that we just don't write so much. Like they were trying to save ink at the printer, and that literally could be true. Pre-internet, right? And so when I have a multi-dimensional integral, I just write one little integral sign and a d tau. Okay, now let's break this down. Oh, by the way, I forgot a pen, so I'm using the pens that I left here before, like little breadcrumbs. So yeah, but we might end class a little early. Hopefully not. Okay, so now remind you that a wave function for hydrogen atom is radial. So we've done that to death over the last 2 lectures. Note that I've labeled it with an N and an L, so remember that the radial obviously depends on the N quantum number. That's its quantum number. And L is part of the Hamiltonian, so of course it affects the solution. There's no M dependence. I've written that as a complex conjugate. There is no letter I. Radial wave functions are not complex, so it doesn't matter. But I'm just putting a little star on there just to be exact. The angle parts, the spherical harmonics, remember, get the little letter Y for whatever reason, I don't know. They get a letter Y, and you need to know L and M. Remember, if M is like 1 or minus 1, you end up with an e to the I phi or e to the minus I phi. Those can be complex, so it gets a little star. Now, any question I ask on this, of course, I'm going to give you the wave function. All right, and then here's the non-complex part. And now here's the thing I really wanted to get to, was to point out that this d tau, which hides the partials of 3 dimensions, r, theta, and phi, you got this Jacobian deal. So don't forget that. And when you, of course, do this integral, you're going to do each variable by itself, look at an identity, and then just multiply the, it's like making an omelet, right? You're making 3 things at once and you just add them all together. And actually, you multiply them all together, right? Now, the reason I'm bringing that up, there's 2 things about that. Don't write this down. Don't write this down. I just want to point out to you something. And I mentioned this last time, but I don't want you getting worried about this. But when you see radio... Oh no, I really should have not made sure I had a working pen before class. Okay. When you see a radial wave function, so my handwriting isn't good today, they have two different normalizations. So I'll call this n prime. So I mentioned this to you last time when I was looking up radial wave functions. You see two different sets where they're normalized differently. One can be, now hopefully you do remember this. You know that a normalization, here let me write it like this so it's not, so you know that I'm doing 1 over. A normalization is 1 over the square root of this, right? Because this should be, with the normalization constant, this is 1, but if you don't know what the normalization constant is, you do this. So you would have an R and an angle part, R and an angle part, right? So, okay, now of course that's what it should be because that's the full wave function, but there is another type of normalization that you often find. That's actually what I wrote in class, where what you do is you simply don't include the angle parts. And it ends up being an R squared dr. Whereas this one would be R squared sine theta dr d phi d, yeah, the theta and all that. Okay, so they're not the same, right? They're awfully close, but they're not exactly the same. And again, you don't have to, I see some of you writing down, you really don't have to write this down. I want to point out that the philosophy behind this is that there's so much about the radial wave functions that are way more important than the angle. Remember that they determine the energy. This is really the interesting part of electronic structure. And so you often do problems by itself, in which case you just completely forget the angle parts are there. And that makes sense to me. What I don't like is that it's an approximation. The angle parts are there. And so when you see these guys, it's because it's assumed that you did everything properly with the angle parts, versus if you're an expert, you know that you can actually ignore the angle parts. I personally would prefer to do it this way, even though it's harder, because you can't ever screw up. Whereas with this, you have to know that the angle parts have already been taken care of. So anyway, I just wanted to point that out. And what I'm really trying to do here, by the way, is get you really used to doing these integrals, because when it comes to spectroscopy, you've now got yourself kind of an operator that's not so hard. So remember that when it comes to spectroscopy, it's all about the difference. I'll spell it out. Did I spell that right? My spelling is terrible. Okay, it's about the average difference dipole. Now the dipole, by the way, and let me see, I think that's minus E times, well here, I'll just spell it out, X, Y, or Z. And that's just because, right, now think about, we're doing this for hydrogen. You've got yourself a proton, you got an electron, hey, that's a dipole. At any given moment. Now, if you were to sit and look at a hydrogen atom and have some kind of little meter, it would average out to 0, but at any given instant in time, it actually has a dipole. And absorption of light is not instantaneous, but it's really freaking fast. By the way, the fact that light absorption is not instantaneous is the subject of the next problem set. A couple of questions on the next problem set. It's kind of fascinating how that works, by the way. But absorption of light is so quick that at any given moment, the proton is here, the electron is there, and you got yourself a dipole. If dipoles interact with the electric field of light, this is why this works this way, the electric field of light interacts with that dipole, it also has to absorb the energy, it also has to take into account the angular momentum of light, and yada, yada, yada. Now notice that I also wrote this in the average value way. Okay, so that means we're going to be doing an integral, that's why I'm trying to emphasize all this stuff. Second, and I didn't say dipole. If we just did dipole moment, let's say I didn't say difference dipole, let's just say it did dipole. Everything's 0, right? S state, does an S state, what do you think is a dipole moment? It's just, it's round, right? How could I have round have a dipole moment? And I believe that that's also, yeah, what's wrong with me? That's also true of P and D states as well. Now I know that we think of those as not round, but they're still symmetric, right? A p-state's not round, but it's like a little barbell, but there's still two sides that cancel out. So nothing is dipolar, but what you're doing is a difference dipole. And for one, I don't know what the point of asking the dipole moment of a ground state is, or the p-state or whatever. The second thing is, if you absorb light, you can't stay in the original state. So your final state has to be different, and that's why the difference dipole, I'll just keep writing down, the difference dipole is going to be, here I'm just going to use some little shorthand, and let's see if I can actually find where I had in my notes, because clearly I'm a little off here. Let's see, okay, so I'm going to write this out in a little bit. I'm going to do a little bit of shorthand, and then I'm going to write it out longhand, because that's what you're going to have to do on the problem set. And of course, I make sure that it's not like absurd. There's a bit to it, but I break it down into little parts, and you've seen me do that a zillion times. So now I've got to do a lot of breaking down with this. So I noticed that when I write a psi like this, I'm talking about the radial and angular, and I'm just abbreviating it that way. I'll write out the whole thing here in a second, but I have another thing to talk about, which is the x, y, and z. Okay, there's two about the dipole moment being x, y, or z. Sorry. I was actually describing difference dipole. The point of that is that the initial wave function is not the same as the final wave function is not the initial wave function. Okay, now the thing that this does is, for one, it's sensible. If this thing absorbs light, it has to change state. It has to, and that's because it has to absorb the energy. Different states, you can't absorb light and be in the same state, because then technically there's no energy. You can't account for energy. It's just plain sensible. So what you can do with spectroscopy, though, is, and I also said this last time, let's just say the initial state is the 1s, right? It doesn't have to be. Chemists, physical chemists, physicists, for really 80 years, I'm about to say 100, just like, oh, it's 100 years. 80, that's actually accurate. For 80 years, we have been able to put hydrogen atoms in a gas chamber and poke it with light. And we know full well how to, of course, make it in the ground state. That's easy. But we can also put them in excited states and then do more things on them. So the initial state does not have to be a 1s state, but that sure is easy. And that's, if you don't try, that's what you make hydrogen, that's what you're going to be getting. So for the purpose of this class, let's just call it the 1s state. Now, what you can do with all this spectroscopy jazz is figure out what the final states are such that the difference dipole is not zero. That brings me to another point. The whole point of this is 0 or not. Remember I said this last time. 0 means it doesn't absorb light, so your experiments on spectroscopy of the hydrogen atoms do not contain a component of 1s to that whatever final state is. Say, let's call it 2s. Here's a hint. 1s to 2s is a difference dipole of 0. So when you do spectroscopy of a hydrogen atom, and you see all kinds of absorptions, maybe you're doing fluorescence spectroscopy, and you see all kinds of fluorescence, none of them are from a 1s to 2s transition, because 0. So anyway, this, and I'm kind of foreshadowing here, this is what this does. Again, we're assuming this is 1s, this could be whatever, and we're looking for all the whatevers that are not 0. That is what's going on in our spectroscopy. Now we understand our spectroscopy, which is ultimately the goal of all this. Okay, still a lot of words, and one more thing before I actually do it. Okay, now, I'm getting out of order. Okay, so the dipole is x, y, or z. E gives it units. I never keep track of that. I think there's a minus sign. I don't even remember that. I don't really care. Doesn't matter. We're just looking for 0 or not. E and a minus sign don't matter. I want to point out that, and I said this last time. Here, let me draw a little round, like a 1s state. And here we got some axes. I'm just trying to make it look cool. And what we've got is we can have, what would this be? I'd call this X polarized light. So this would be X, Y, and Z. So this is technically X because it's like coming at you like this. And then I would have Y polarized light because it's actually slinking along the Y. And then Z polarized, kind of ran out of room, this would be Z. Okay. So as I mentioned last time, that if we're going to use, let's say Z polarized light, we need to translate it into R, theta, and phi. So well, actually here, let me write it right here. That's a little bit more simple. And as I mentioned, that is R cos theta. Now that's just high school trigonometry for you. That's spherical coordinates for Z. But we happen to know these in wave function land as R times a spherical harmonic. The spherical harmonic is L equals 1, M equals 0. That's code word for cos. Spherical harmonic, L1, M0 that's a P state, that's a PZ state. That is code word for Z. It's the same thing as Z. Okay, X is, let me write these down. X, now you've done this before on homework. R, this is a little bit more complicated. You have to do a linear combination. Linear combinations, don't write this down, but linear combinations, for any function that is a valid solution to the Schrodinger equation, for whatever Schrodinger equation, hydrogen atom, helium atom, whatever, you can combine them. You make linear combinations, and it's perfectly fine. Those are solutions too. And maybe I'll explain a little bit more about why that's useful. Okay, so X and Y, if those represent light, then those are the functions. Those are the operators. And one thing that's cool about that, and then I'm going to plug these in, and then we're going to see some more stuff. What's cool about this is not only have I got an operator. Remember I told you at one point that you're going to know 20 operators by the end? That's probably an exaggeration, but here's another. This is technically an operator. You know a couple now. It's also in the correct cosine R, it's the correct spherical harmonic, so it can be integrated into our wave functions without blowing our heads off. Like when we had to convert momentum into cylindrical coordinates, that was that was awful. Just not complicated, just algebraically a nightmare. That's cool, but the last thing I want to point out is light has angular momentum. Remember that there are some big rules in our universe, like speed of light is constant, energy is constant, momentum is constant. Light has momentum, but you see the momentum of light is incorporated into the operators. So it preserves so any issue with conservation of momentum is preserved by the fact that the operator have angular momentum and the right angular momentum of light. Light happens to have 1 h-bar of momentum. And the fact that our operators have that same momentum makes all of this work hunky-dory. So when you get a non-zero, now don't forget that, a non-zero difference dipole deal, not only is that a spectroscopic observable, and remember our goal is to explain our spectra, it also is going to correctly conserve the momentum of light. So you've conserved the energy of light, you conserve the momentum of light. You better do that. Better do that or it doesn't work. Excuse me, frog in my throat. Okay, so here's some shorthand for how to do this. Again, it's stupid simple. Of course, the final wave function is not the initial wave function. That's idiocy. And so now let me write this out into parts, and the parts are now going to be revealing. I'm going to do the radial, so there's a single integral there. There is going to be, now I'm going to have to distinguish the initial and final. Of course, the final better have a little complex conjugate, not that it matters. Remember that there's two quantum numbers that define that. Okay, I've got an R. Okay, but I've got an r squared in the Jacobian, so I've really got an r cubed. Whoop-de-doo. Okay, r cubed, there we go. And then I've got an initial, of course it's a 1s state, but just for the hell of it, I'll just call it, I'll give it a little letter I, just so I'm not necessarily deciding that. Okay, then I've got two integrals. So here's something that's also very revealing. I tell my grad students this. When it comes to quantum mechanics on real things are made of atoms, so I'm talking about quantum mechanics on chemicals, molecules, atoms. The radial is never hard to work with. This, you can deal with this and you're just learning, that's great. The angle parts are a different story. The angle parts make this, God, unbelievably hard. You know, I'm supposed to say challenging, by the way. It's hard. It is the angle parts where, oh man, this is where you just get wiped out on an algebraic zoo that just would blow the head off of Einstein, who did not believe in quantum mechanics, by the way. Hopefully I'll get the order of integration correct. I'll double check that. Okay, so what are we doing? All right, so and I'm going to do Z polarized light because that's easier. Okay, final L, initial M, final L, initial, I said that right. Just check to see that I said that right. Okay, so that's the wave function. Now, again, I'm going to do Z polarized, so write that down. So that is 1, 0. Notice I'm not saying that's initial or final. That is from light. That is, yeah, it just is from light. Okay, and then I've got the initial state, again for a 1s state, that is simply a constant, right? It's just a normalization constant. Okay, and now I've got to make sure, Jacobian, DLE there. Then let's see, okay. And you folks remind me of this.
So if it's 0 to 2 pi first, that's
Theta. Theta is this one, right?
you define that as 5.
Well, not in chemistry. That's theta. Now remember, folks, I told you, I actually are in chemical. Wait. In chemical engineering, do you define theta this way? Yep. Theta is this way.
Yeah.
Good. Okay, so we do that too. Mathematicians do it the other way, which is, God, what? I mean, why? Why do we? Somebody got in a fight with somebody else and had to like.
Wait, but if your Z is defined as R cos theta, then theta's got to be trapped between.
No, wait. Did I screw that up? Yeah, yes. I did. No, I screwed that up. No. That's right. That's right.
So the thing going from 0 to 2 pi is phi.
That's right. Sorry. Wait a minute. Theta is this one, right?
Yeah.
That's right. Oh, okay. Don't let me screw. I get confused because, yeah, I mean, I have to deal with both all the time. This is theta, this is phi, because phi, you know I always get confused is because when we start out with the 2D rigid rotor, its angular momentum is in the z direction, but it's rotating in the xy. Remember even I said to you when we covered that, I was like, gotta keep that straight. I was really saying that to myself because of what just happened. Right, okay. Theta is this, phi is this. Okay, and I know that phi is definitely 0 to 2 pi and theta is 0 to pi. And don't worry about, you don't memorize this. I have it straight for you on the test. This is a detail. I don't want you losing points on details. That's stupid. I'm going to give it to you. If you screw it up after that, then that's why some people shouldn't get A's. Okay, so there you go. All right, now remember the name of the game from here on is, I'll have you do this on your homework, and so you just plug in stuff and see what happens. By the way, what's kind of interesting is apparently the spherical harmonics, triple products of spherical harmonics are so common, you can find like Wikipedia, you can find a table of like, okay, if you're fully integrating 3 spherical harmonics, here's, all the permutations that give you 0 or not. And because, I mean, we're doing them now, apparently they show up in a zillion other things. I'm sure the engineers know of other instances that I don't, but anyway. Okay, now again, the name of the game is 0 or not. Now it turns out this is never 0. Now remember that if this was an r squared, you would always get 0, right? Because then, now the reason that is, remember that this is r cubed because I have an operator and a Jacobian. Okay, that's why it's r cubed, right? That's simple. If I didn't have an operator, this is just the integral of one wave function and a different wave function, orthonormality 0 every time, right? So don't forget that orthonormality deal. Two wave functions integrated is always 0. The same wave function integrated, complex conjugate, blah, 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 is always 1, orthonormality. Okay, but now the thing is that normally my gut instinct would have said 0, but oh wait, no, that's not r squared, that's r to the cube. Turns out it's never 0. Now that implies that any transition is possible as long as you absorb some energy. Okay, but now spectroscopically we know that's not true. As I was just saying a second ago, the radial is never the hard part of this, it's always the angular. This is the guy that decides whether it's 0 or not. Okay, so let's look at this. Okay. Now remember, not 0, and that's a little weird, not 0 is like a double negative, right? But just kind of remember, it sounds awkward, but that's what you want to know. Not 0 if delta L is plus or minus 1. There you go. And so we call that a selection rule. A selection rule. Don't forget that. That's kind of important. You know, I don't like you memorizing words and little things like that, but that one's kind of important. Okay. Now, another thing is, though, it kind of makes sense. Light has L of 1. So if you're going to account for that via absorption, if the photon disappears, its angular momentum can't. Angular momentum is conserved. Now, notice how, it kind of like gives me goosebumps a little bit. Maybe I'm just revealing how geekish I can be. The operators being polarized light, which is a good description of light, naturally have angular momentum. The results naturally account for angular momentum of light. It all works out perfectly without you having to turn any knobs or buttons. You just start with the Schrodinger equation, convert the damn thing into radial, add a 1 over r for the Coulomb potential, solve everything. Light's polarized, you know that, and all of this has worked out perfectly. Every bit of it worked out perfectly. Light's energy is conserved, its angular momentum is conserved. Now, here's the detail. Don't write this down. I don't care. This is when, if we were to teleport ourselves to the 1950s and we just learned quantum, we're just getting these great vacuum chambers, and we're doing like really high resolution experiments for the first time, there's other details you can start whittling out of this, and that is the delta M selection rule. Okay, now don't even write it down. Don't even write it down. I don't care. I don't care about this. This is a really minor detail that if you go into grad school and you become a spectroscopist, you do need to know this. So I want you to know that this exists, but I don't think that's going to happen. So whatever. Okay, delta M is 0 for Z polarized, but it has to be plus or minus 1 for X, Y polarized. Not a big deal. Not a big deal. Besides, you know what's kind of silly about this is how do you know which way is up for a hydrogen atom? You don't, right? I know this is up because of the force of gravity, but atoms don't feel gravity. It's too weak. Now, where this does matter, though, if one is really deconstructing a quantum mechanical object and you really feel like you need to get all this jazz down, you put it in a magnetic field. When you put this in a magnetic field, electrons are magnetic, and remember that when they spin around, they generate a magnetic field. That's how magnets work. The electrons spinning around in the magnets, right? They spin around in a circle. This one's not spinning around in a circle, and so it's not affected by a magnetic field, but these guys are. So what happens is if you put it in a really, really obscenely strong magnetic field, then these states are no longer degenerate, and then you pick that up spectroscopically. And the reason is to do that is if you really feel that you've got to know the very, very small details of whatever hydrogen atom, or not hydrogen atom, not now, but whatever thing you've chosen to study. Let's see, I guess that's about it. Yeah, that's about it. You know, all spectroscopy comes down to just this, all spectroscopy. It just depends. The operators are basically always the same. It's just a dipole moment, because light, whether light is a radio wave or optical like we see, or X-ray, it's all a different dipole. Where nuances kick in are what is your initial and final state. So I have done, this is electronic spectroscopy, which is UV-Vis X-ray spectroscopy. UV-Vis spectroscopy, but now X-rays are like a big part of research nowadays, and those also involve electrons. If I'm talking about, if these were vibrational wave functions, now remember, these are electronic wave functions because I'm describing electrons, but we've covered vibrations. If I simply put vibrational wave functions here, then you can figure out those selection rules. You can figure out, yeah, I mean, once you do that, you kind of, when you get selection rules, you really have everything, right? You know the energies from the Schrödinger equation. If this is zero or not, tells you whether they absorb. You then calculate the energy difference, convert that to wavelength, and then look at your freaking spectrum and see whether it's there or not. Done. That's really how the game works. If these were rotational wave functions, which we'll get into in a little bit, there's not. Well, anyway, we've covered some rotational wave functions. What am I saying? Then fine, that works too, and you find that the energy differences are in the microwave region of the spectrum. That's why microwaves work. They cause water to rotate, by the way. And so, again, you can take an entire class on spectroscopy, and you start on day one with this, and then everything is a detail from there, and you can fill up an entire semester. For this class, I'm just going to talk about this, and then I'm going to tell you about the forms of spectroscopy, but without doing anything more with this, because it's all just a matter of crossing your T's and dotting your I's and whatnot. And I'm going to have you do homework, and you're going to have, next homework, you got to do some games with this, and I'm just kind of checking your competence, really. I'm certain you can set this up, look at the integral tables, which are provided, write down what you see, and collect points, right? It's like the world's stupidest pinball game. All right, now, so with this, I don't think I'm going to breach spectroscopy again. I'm a little unusual that normally most people who teach the class talk about this ad nauseum, but I mean, everything is a detail from here. I just don't see the point, especially if there's some other things. You know, if I can cover a little bit of a wider net, I tend to rather prefer to cast a wider net, and at times go into a little bit less detail than the opposite. Again, for grad school, like I'm helping our faculty design the spectroscopy course for grad students. You folks can take it if you felt like. You can, you know, I don't know that that's a great idea, but I mean, you could. And I'm helping that person design the course for that. And it's really some details into that. And so, again, you can take a whole class on this. So if I'm just going to leap past that, now we're going to get into a hideously different subject, Okay, and I use a lot of shorthand because I'm an idiot who forgot to use pen. It's in my old pen. I left the cap slightly off, so it should have been okay with the cap slightly off. Anyway, multi-electron wave functions. All right, I'm going to write the Hamiltonian, and then I'm going to point out something that's devastating to our ability to do quantum mechanics, which from your perspective may be kind of cool, because all this sine, cosine stuff is gone, aside from your homework and tests. I guess that's not gone. What is very important are spin wave functions, right? So recall that, let me write down, let's look at a 1s state, and you know that for 2s, you got this, you got 2p. Notice that they're degenerate, because remember that only the n quantum number affected the energy, and that means that S, P, and D are all degenerate. Now, you learn differently in freshman and inorganic. you guys, engineers, remind me, did you not take inorganic?
No.
You didn't? God, inorganic is like one of our best classes. It's actually really fun. And you also get a big dose of quantum in that too. God, that's kind of a shame. And not just because I'm a chemist, it really is a good class. Especially Cabana and Mancat are like really good at that too. So it's just a flat out enjoyable class, even if you're not necessarily into that. Okay, regardless, if you learned a little bit about crystal field theory, I do have actually a couple of chemists in here, all 5 of you. You learned that these can get split up, but that's for reasons that I'll explain in one more week. Regardless, the hydrogen atom has all these degenerate. So notice that, again, now this is a high school deal. Now you learned that when you start filling electrons into orbitals, you do spin up, spin down, right? And if I do this guy, if I have more electrons, I do the Aufbau principle. Again, this is a high school deal. And then if I have more electrons, 4, 5, 6, 7, I've done nitrogen. This is nitrogen, oxygen, chlorine, neon. Anyway, I think I have it. I don't know if I wash up on a deserted island, can I rewrite the periodic table so we don't have to rediscover it? I don't know. I should be able to. I don't know that I can. Anyway, so that's how we keep track of electronic structure. That means I have to have spin wave functions, and when I have spin wave functions, I can then write multi-electron wave functions. And we're going to mostly focus on H- and helium, just because. And everything else, again, is just a nuance from there. Okay, now here's where this, I have to admit, is legit kind of cool. And you've kind of seen this before. Remember for the 2D rigid rotor, what was the radial wave function? 2D rigid rotor.
It was constant.
It was a constant. So does the wave function exist?
No.
Does it? Kind of, right? Kind of. That's actually the right answer. I won't write this down. This is another of those times I don't want you writing it down. I just want you thinking. All right. Kind of. Because if you say that there's no wave function, then there's no information. There is information. If I ask you to do a 2D rigid rotor problem, I'm going to tell you, the mass of an electron. I have to give you the mass, and I have to give you the track width, the radius. I have to give you the radius. So there's information there. And the way to express that, and no fooling, is to say that the radial wave function is 1 nanometer. And that's correct. The question is, like, wait a minute, so is that R? No, R is R. And also, if you say the radial wave function is R, that implies that R can change. No, it's just 1 nanometer. And then you may say, well, that's not a function at all. My answer, that's correct. It's not a function at all. It's just information. Yet, that is the answer. Wave functions are not always e to the I, R, phi, cosine, d, theta, blah, blah, blah. They can just be straight up information. Okay, spin wave functions. Here is the spin up wave function. Alpha. And now, who knows what alpha is equal to? In terms of, all right, so is this going to be a, e to the I phi? Or e to the minus I phi? Alpha is equal to alpha. No fooling. There is no functional form. Alpha is just alpha. That's spin up. And beta is spin down. And that is it. Those are the wave functions. Alpha is alpha, beta is beta. Now, they actually do things, and I'll show that in a little bit, but I just want to get you used to the fact that we actually have no mathematical form for these wave functions. Now, they do things, and again, I'm going to get into it, so that it makes a little bit more sense. This probably makes no sense at all, but I swear to God, we have no e to the I phi for this, no sine theta for that. This is what they are. Now, one reason I think that this happens is I mentioned when I was talking about spin, I know you know what spin is, but I put a little bit more context into it for you. I mentioned to you that it's a form of angular momentum, works just like angular momentum, but with an L of a half. So this little L of a half is kind of weird. Remember that. So S is 1/2 h bar. So the sub s's are plus minus 1/2 h bar. Plus is alpha, minus is beta. So these have angular momentum. If I'm writing this out like this, it's angular momentum. So why no functional form? It's because it's not like rotating. Remember that spin is due to something that we don't know what it is. It's not rotating. It's not that the electron is rotating. So remember, I'm talking about electrons. They're spin up, spin down. That's the amount of the spin angular momentum they have. They behave as though they're rotating on their axis like a basketball player turning a basketball. It behaves exactly like that, but it is not that. We don't know what it is. We've never figured it out. Now, if we don't know what it is, how do we have a wave function for it? A sine and a cosine and blah, blah, blah. We don't know what it is, so we don't have a functional form, but that kind of makes sense. And I'm always curious whether a Stephen Hawking will come along and figure out what the heck these really are, but for now, we just know them as alpha and beta. Now, recall also that I had that extra lecture on I labeled it the real Schrodinger equation, time-dependent Schrodinger equation. I also mentioned the Dirac equation, where you actually end up with a description of spin naturally falls out of the Dirac equation. I don't think I put that correctly, but anyway, so we don't have any functional form of these. All right, now what? What else do I want to say about this? Okay, so now with this information, let me write out the Hamiltonian and show you another neat thing, and then we're just about out of time. So I'm going to I'm going to introduce another symbol here. It's not too hard. Okay, M1 would be mass 1, assuming it's an electron, right? So it's an electron. Now, you folks, you probably know what this is, right? Del squared? Mm-hmm. Yeah, double ddx squared plus dy squared plus ddz squared. Put it in r theta and phi. You know what that's about. That's it. Okay, so I'm just going to call it del squared. Okay, and then that's for one electron, mass 1, the first electron. Of course, when I'm talking about electrons, I guess maybe it didn't have to be, maybe we talking about quarks or some crap. Okay, minus e squared. All right, so I'm clearly writing Coulomb's law, and especially when I write down 4 pi e naught, the permittivity of free space, the making the units work. Okay, so I'm seeing Coulomb's law. Imagine I threw this at the test and I said, hey, where does this come from the multi-electron wave function? This is the interaction of electron 1 with the nucleus. I can tell because I've got, each one brings an E of charge, but one of them is minus. So it's an energy lowering, there's a minus sign, right? So that's where that comes from. Now I know you think this is like, well, of course that's where it's from. Well, I'm gonna rattle your cage here in 1 second. Okay, I've got a second electron, and it has kinetic energy too. And of course that sucks. And that electron interacts with the nucleus just like the first one. Okay. And voila. Plus e squared. Now, of course, plus, that means that these two things have the same charge. Whether they're both minus or both plus, you're going to end up with plus. 4 pi e naught, of course, is a sign that I'm talking about Coulomb's law. And then I've got this deal. Let me, there's a couple ways to express this. I like this one because I think it's the most accurate. Absolute value of the difference. All right, so what is physically happening here? Why did I write this? Electron 1 and electron 2 are? Yeah, they're repelling each other. Of course they do. Of course they repel each other. So, E1 and E2 repelling. Okay, now, here's the major problem. Electron 1 coordinates. All right, this is a Hamiltonian. I need to separate it. Electron 1 coordinates, electron 1 coordinates. That says to me that the total wave function is going to be 1 for R1. And look, I've got electron 2 and electron 2. That means I've got another wave function. Now I'm going to have to be, now notice this. definitely pay attention to this, put a star, this is important. I've written psi1 R1, and I'm going to write psi2 R2. Now, it seems like R1 and R2 would have been enough, but no. Why? Here, let me get rid of this jazz. It is true that I could be describing something like this. I could have one electron in a 1s state and another electron in a 2s state. I can describe anything I want to, and never forget that the physical chemist's ability to put atoms into different states is actually quite good. Okay, so I've done that. Now, real quick, one second. Okay. What about this? Now, remember, I'm separating. If I'm separating, I can write separable wave functions. So basically, I take the hydrogen atom wave function for one, and I take another one, and I multiply it, and I just multiply it, and I just label it with a 2. What about this? Separable? No. So what do? What kind of trick do I use? Huh? If you can figure that out, you win a Nobel Prize. No one's ever figured it out. They're not separable. The wave function is not separable into R1 and R2. No one has ever figured this out. Real quick, so you know what we do? Anyone knows what we do? You just use it anyway. It's wrong, but we write them out this way anyway. But now there's a consequence to that. Guess what that is? R theta phi, analytical solutions don't exist. We force the solution to look this way, but we're also forced to solve the wave functions on a computer. The wave functions become giant tables of numbers as opposed to cosines and e to the minus r. So I'll talk more about that next time. I know it went over. So, all right,